Welcome back. Unit 5 of our journey through advanced topics. This unit is going to focus on what we in the mathematical world define to be the real number system. Our first lesson is on the inaugural set of numbers known as the natural numbers. As you can see, there's quite a bit of vocabulary for this particular lesson, but it is integral to our understanding of the real number system. Today's learning objective includes we are learning about the natural numbers so I can find the greatest common factor and least common multiple of two numbers. I'll know I've got it when I can write the prime factorization of a composite number. Let's begin. N equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Keep counting as high as you possibly can. We call those values the natural numbers. And if you think back to when you were a wee lad, as soon as you were able to count items, you started with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is a distinct difference between this set and a set we'll talk about in our subsequent lesson that includes 0, but this set of numbers, 1, 2, 3, 4, 5, etc., would be known primarily as the counting numbers. Natural numbers that are multiplied to get a product are known as the factors of that product, and we say that a natural number A is divisible by another natural number B if the division results in a remainder of 0. So seeing as this is our first foray into this lesson, I'd like to see how much you can properly recall. So list all the factors of 24. Try and use the definitions that we have here on this screen. Remember, a number is considered a factor if it can divide into the number 24, and there will be a remainder of 0. I'll give you an example. The number 2 works because 24 divided by 2 is 12. Therefore, 12 also works for the same set of reasoning. There are some additional factors, and I'll leave those for you to identify. Continuing on, we add classification to our numbers, but a natural number greater than 1 is called prime if it has exactly two factors, 1 and itself. So a number that always stands out to me is the number 17. 17 is only divisible by itself and the number 1, so we would consider 17 prime. And we would say a natural number greater than 1 is called composite if it isn't prime. That is, if it has at least one factor other than 1 and itself. So here on our right side, we have a table with these particular values, 25, 17, 12, 31. And I'm asking for you to identify which ones are prime and composite. I clearly just said that 17 was composite, therefore I can help you out with that one. But nothing too strenuous here, just a little bit of recall. Which brings us to our next talking point. Every composite number can be written as the product of prime numbers in exactly one way. The order is unimportant due to the commutative property of multiplication. So in this instance, we want to find the prime factorization of 100 and 140. I'll help with 100. So I know that 100 will factor to 10 times 10. I further know that 10 times 10 can factor as 5 times 2. That's for the first 10, times 5 times 2. That's for the second 10. In this instance, I see that 5 and 2 are considered prime, and every composite number can be written as the product of prime numbers. So since all of these values here are prime, all I can really do is tighten up my notation And this would be the prime factorization of the number 100. 2 squared times 5 squared. If we expand that, 2 squared becomes 4, and 5 squared becomes 25. 4 times 25 will give us 100. On your own, I would like for you to prime factorize 140. Be sure to hit the square root button. That way your math type can be accessible. Now, why is it important for us to be able to construct the prime factorization of an abundance of numbers? There is a way for us to use the prime factorization to determine the greatest common factor. So in this instance, we have the numbers 18 and 24. And here are all their factors. We can see that they have 1 in common. We can see that they have 2 in common. We can also see that they have 3 in common. We can also see that they have the number 6 in common. So obviously, our greatest common factor would be 6. This is the highest number that can divide into 18 and 24. But what do we do in the instance when the numbers are huge? What if we have 300 or 742? Right? It becomes a little bit more arduous, a little bit more tedious, and this is where we would simply rely on the prime factorization. So the greatest common factor of two or more numbers is the largest number as a factor of all the original numbers. Our process would include writing the prime factorization of each number. We want to make a list of prime factors that appears in each prime factorizations. For prime factors with exponents, and if let me demo the prime factorization while we're typing this. So 18 has a prime factorization of 3 squared times 2, and 24 would be 2 cubed times 3. As we can see here, if the greatest common factor is a 6, right, we would, for prime factors with exponents, and now they both share prime factors, we want to choose the lowest power that appears in each. And we would say that the GCF is the product of the numbers we listed in step 2. So going back to our situation here, we're going to look at the prime factors that appear in each. So we clearly have a 2 and a 3, and then we want the lowest power. So I have a 2 to the first here. Nothing's going to get lower than a 1. We have a 3 to the first here. And then we take the product, 2 times 3, we wind up at 6. Okay. This is the process that we want to utilize when we have numbers that are extremely large. So at this point in time, I'd like for you to take an opportunity to find the greatest common factor of 40, 60, and 100. It might be a little bit obvious using your intuition. However, I'd like for you to kind of take some time to practice and hone your skill set, so that way, in the event that these numbers are not so straightforward, you can still apply the concept. Two numbers whose greatest common factor is 1. That means there is no common factors. We call this number relatively prime. Now let's change course and talk about the least common multiple. So a multiple is when we take a particular value and we double it, triple it, quadruple it, times 5, times 6, so on and so forth. And when we're looking for the least common multiple of two numbers, we're looking for the number that they both coincide with that is the smallest. So for numbers 4 and 6, we can clearly see that they have 12 in common. We can clearly see that they have 24 in common. And if I extended this table here, they would have 36 in common. So it's pretty obvious that our lowest common multiple is the number 12. But how could we apply this process in the event that we did not have numbers like 4 and 6, and we had numbers like 406 and 512? Well, the least common multiple of two or more numbers is the lowest number that is a common multiple of each. In other words, and this is redundant, the lowest number that is divisible by all of the numbers. So once again, it requires writing the prime factorization of each number. So let's do that while we're typing out our steps here. Right, the prime factorization of the number 4 is pretty straightforward, to the second power. And 6 would be 3 times 2. So in this case, we want to list every prime factor that appears in both, all. So whether they have them in common is not important here. We have a 2, so we're going to list the 2. We have a 3, even though the 3 is not a factor of 4, okay, we need to include it in our multiple. So let's type that into our notes. For prime factors with exponents, whereas with the greatest common factor, we selected the lowest exponent, we want the highest power. In this case, the highest power for the 2 is the second power. And if we multiply this expression correspondingly, we get 12. So that part at least remains the same. But in both of these situations, step 2 details the specific process that differs between these two concepts. So of course, I like to see you give it a shot with the numbers 24, 30, and 42. Okay, document all your work. Make sure you list out your prime factorizations, and then for the LCM, you could group the terms that you're supposed to. If it was a little shaky, I would go back and rewatch the last 90 seconds of this video. Checkpoint 3 has you working through an application problem where we have hot dogs coming in packages of 10. Most hot dog buns come in packages of 8. What's the smallest number of packages you can buy of each so that you end up with the same number of hot dogs and buns? This is a true story, as I hosted a small get-together this past summer and coincidentally was staring at my package of hot dogs and the package of hot dog buns and needed to buy way more packages than I did hot dogs. And that's where we'll pause this video and pick up tomorrow together in class to hash out our enhancement opportunities. See you then.